Okay, let's unpack this. For the longest time, many of us, well, we had this picture in our heads, right? Almost like a textbook diagram of how planets are born.
Uh-huh. A neat little disk of gas and dust.
Exactly. Slowly, steadily, everything just kind of coalesces into planets. But get ready, because the new views we're getting, they show it's way weirder out there.
Weirder, faster, much more dynamic than that tidy picture suggests.
Yeah. So today we're diving into a whole bunch of new research. We're talking papers, observations, the raw data.
And it's really challenging some fundamental ideas about planet formation.
We've got amazing new stuff coming from telescopes like James Webb, ALMA, the Very Large Telescope. They're giving us these incredible peeks into stellar nurseries.
Yeah, and what's so fascinating really is seeing direct evidence that just doesn't quite fit the established theories. Sometimes it pushes against them quite hard.
Right.
So our mission for this deep dive, essentially, is to explore these new findings, see how they're refining things, maybe even shattering old ideas.
And connect the dots, right? What does it all mean for the kinds of planets out there? And I guess for our own solar system, too.
Precisely. That's the goal.
Okay, so we're going to find out how planets might be forming, like, incredibly fast.
Yeah, surprisingly fast.
Discovering cosmic environments with totally unexpected chemistry.
Definitely some chemical curveballs.
And even realizing these flat planet-forming disks, well, often they're not flat.
Nope. Often warped, bent.
So yeah, expect some aha moments. We're heading into the universe's, like, busiest construction zones. It's all about rewriting those cosmic blueprints.
That's a good way to put it.
All right, let's jump straight in. First up, the clash of creation theories. Now, for ages, the main idea, core accretion.
Yeah.
That was the front runner, yeah.
It was, and still is, a very important theory. The basic idea is slow and steady.
Like a cosmic snowball, right. Little dust grains stick together, get bigger, form a core, then grab gas. Patient work.
Very patient. You build from the bottom up, small things accumulating into big things.
But now you're saying new observations are kind of turning that on its head, or at least offering a serious alternative.
Exactly. Core accretion works well for many things, but we're seeing strong evidence for another way. Gravitational instability.
Okay, gravitational instability, less snowball, more. You call it a snowplow.
Yes, that's the analogy. Instead of tiny bits clumping, you have large parts of the disk itself becoming unstable and collapsing directly into a massive object like a giant planet.
Wow. So top down instead of bottom up.
Pretty much, and much, much faster. The issue was actually seeing this happen, getting direct evidence was tough. So core accretion held the main stage.
Until now. What's the new evidence look like?
Well, a key piece comes from MIT. Assistant Professor Richard Teague and his team looked closely at the AB Origin system. It's about, 530 light years away?
Okay. And what did they find there?
They mapped the gas movement within its protoplanetary disk. And get this, the way the gas was flowing, the velocities, the patterns. It matched exactly what computer models predict for a disk undergoing gravitational instability. Whoa, so not just seeing the result, but the actual process, like seeing the snowplow pushing things around.
That's a great way to think about it, yeah. It's seeing the dynamics predicted by the theory in action.
And why is that specific observation such a big deal?
Because, as they detailed in their paper, it gives us a really solid way to form those huge planets, Jupiter-sized or even bigger, that we find really far out from their stars.
Ah, right. Those were always a puzzle for core accretion, weren't they? Too slow out there.
Exactly. The timescales just didn't seem to work for core accretion way out in the cold, sparse outer disk. But gravitational instability, it can potentially form massive planets far out and quickly. So it helps explain those systems.
Changes the odds, maybe, for how common those kinds of planetary systems are.
It could, yes. It really broadens the possibilities. And it's not just a one-off in AB Origin, is it? There's more evidence popping up.
There is. Over at ESO, the European Southern Observatory, researchers used the Very Large Telescope, specifically a new instrument called IRIS.
IRIS. Okay.
And they might have directly seen a planet forming inside a spiral arm structure in another disk around a star called HD 135344.
Seriously? Like caught in the act?
Potentially, yes. They detected light that seems to be coming from the planet itself, not just its effect on the disk. It looks like maybe a Jupiter-sized world, maybe twice Jupiter's mass, way out there, kind of like where Neptune is in our system. Seeing its own light is pretty significant.
That's incredible. And wasn't there another one, V something?
V960 yes.
Yeah.
Also observed with IRIS. This is a really young star. Its surrounding material has these amazing spiral arms, and there are clear signs the arms are fragmenting, collapsing.
Gravitational instability again.
Looks like it. and they spotted a companion object, could be a big planet or maybe a brown dwarf, right near one of these unstable arms. If that holds up, it's another strong case for this rapid, large-scale collapse mechanism.
It really paints a different picture, from slow, steady snowballing to these, I don't know, dramatic cosmic collapses.
It suggests both processes are likely happening, perhaps under different conditions or in different parts of the disk.
And this idea of speed, it seems to be a recurring theme, right? Which brings us nicely to our next point. Planetary fast tracks, like planets forming almost right away.
That's what some new observations strongly suggest. The old thinking, mostly tied to core accretion, was that, building a giant planet takes time. At least 1 million years, maybe more.
Okay, 1 million years minimum.
But new data from LMA, the Atacama Large Millimeter Submillimeter Array,
Oh,
part of a survey called CAMPOS.
Campos.
Yeah, led by Chenghan Shi. They're finding detailed structures, rings and gaps, the kind of things we think planets carve out in disks that are unbelievably young.
Unbelievably young. How young are we talking? Like cosmic toddlers?
Even younger. Cosmic newborns, really. Class 0 and Class 1 young stellar objects. Their disks might only be, say, 10,000 to maybe 300,000 years old.
Wow, 10,000 years. That's practically instantaneous in cosmic terms.
It really is. And seeing these well-defined rings and gaps so early is, well, it's surprising.
Because if planets are already making those features,
Or at least something is organizing the disk that way.
then the whole process has to start much, much earlier than that million-year baseline we had from core accretion models, especially for giant planets.
Precisely. It's a major challenge to the traditional timeline. Now, we need better resolution to be absolutely sure those gaps contain fully formed planets. LMA, in this case, couldn't quite resolve down to, say, Saturn's distance from the Sun.
Okay, so maybe not confirmed planets in the gaps yet, but the gaps themselves are there.
The gaps are there. And their presence tells us something crucial. The disk has already settled down quite a bit. The initial turbulence has died down enough for these structures to form. That environment, ready for planet building, seems to be established way earlier than we thought.
Paving the way for planetary systems to potentially get a really early start.
Exactly. A much faster track than previously imagined.
Okay, so planets might be forming super fast, but what are they made of? Because that's where things get even stranger, right? This brings us to the Great Water Mystery, and apparently a CO2 surprise from the James Webb Space Telescope.
Ah, yes, the chemistry. This is fascinating. JWST's MIRI instrument looked at a disk around a star called XUE-10. It's far away, about 8,000 light years, in a big star-forming region.
NGC 6357. Okay, XUE-10. What's weird about its disk?
Well, the inner part of the disk where you might expect rocky planets to form is loaded with carbon dioxide. But it's almost completely missing water vapor.
Hold on. Lots of CO2, but hardly any water. In the inner disk.
Exactly. That's the opposite of what standard models predict.
Yeah. I thought the idea was like icy pebbles drift inwards, they cross the snow line where water ice turns to vapor, and poof, you get a wet inner disk.
That's the conventional picture. But XUE-10 just isn't playing ball. It's stubbornly dry, water-wise on the inside, but rich in CO2.
So why? What's going on there?
Well, the leading hypothesis, put forward by researchers like Jenny Fridiani and Arjan Bick, involves intense ultraviolet radiation.
UV light. From the star itself, or?
Could be from the host star, or maybe from massive neighboring stars in that busy NGC 6357 region. The idea is this harsh UV bath could be blasting water molecules apart, destroying them, or maybe preventing them from forming efficiently in the first place.
Huh. So the local environment totally changes the recipe.
It could, yes. Or another possibility is maybe the raw materials that dust grains drifting in were just inherently CO2-rich and water-poor to begin with because of the specific conditions where they formed further out.
And didn't you mention something about isotopes, like specific types of carbon and oxygen?
Yes. MIRI didn't just see CO2. It saw uncommon isotopes, carbon-13, oxygen-17, oxygen-18, mixed in with the standard ones.
And why are those isotopes important? Are they like chemical fingerprints?
Exactly like fingerprints. They trace the history and the processing of the molecules. The specific ratios of these isotopes can tell us about the radiation environment, the temperature, how molecules were formed or destroyed.
Okay.
And what's really cool is that these unusual isotopic patterns we see in XUE-10 might shed light on some strange isotope ratios we find in meteorites and comets right here in our own solar system.
Seriously. So studying this distant disk could help us understand stuff in our backyard.
Potentially, yes. It suggests that these extreme UV environments create unique chemical pathways, and maybe some of the material in our early solar system experienced something similar. It definitely widens the range of chemical starting conditions for planets. A planet forming there could be very different from Earth.
Wow. Okay, so XUE10 is weirdly dry. But didn't Webb find the opposite somewhere else, like a surprise abundance of water?
It did. Sort of the other side of the coin. In the PDS-70 system, much closer, about 370 light years away, and known to have a couple of giant baby planets already,
Right, I've heard of PDS-70.
Webb detected water vapor in the inner disk, right in the zone where rocky planets might form, kind of like Earth's distance from the sun,
And why was that a surprise?
because PDS-70 is relatively old for a disk with gas, about 5.4 million years. The thinking was that by that age, a lot of the initial water in the inner disk should have been dissipated or incorporated into planets already.
Ah, so finding water vapor still lingering there was unexpected.
It was. It raises questions. Is this water somehow forming in place right there in the inner disk from hydrogen and oxygen atoms, or is it being transported? Are icy dust grains somehow making the journey from the cold outer disk past those giant planets that have carved a huge gap, all the way into the warm inner regions where the ice turns to vapor?
That seems like a long trip, getting past the giant planets.
It does. So it really makes us rethink how water moves around or persists in these older disks and how planets might influence that delivery.
Man, the chemistry is complicated. Okay, so we've got speed, we've got weird chemistry. What about the actual structure, the shape of these nurseries? That leads us to our last section, warped worlds and eccentric orbits. You hinted earlier that the flat pancake idea is out.
Yeah, that idealized image is definitely getting revised. More LMA data, this time from a collaboration called ExoLMA, has shown that quite a few planet-forming disks aren't perfectly flat. They're subtly warped.
Warped, like bent out of shape.
Sort of, yeah. We're not talking crazy angles, maybe just a few degrees of bending or twisting across the disk, but it's there.
And why would they be warped?
It could be gravitational tugs from a companion star that we haven't seen, maybe one orbiting at an angle. Or perhaps it's internal dynamics, the complex interplay of gas and dust within the disk itself. But it suggests a more chaotic beginning than we pictured.
More messy.
Definitely more messy, less serene nursery, more dynamic construction site.
And what's cool is, doesn't our own solar system have slight tilts? Like the planets aren't perfectly aligned with the sun's equator.
Exactly. The planets in our solar system orbit on slightly different planes, tilted by a few degrees relative to each other and the sun's equator.
So maybe these warped disks we're seeing elsewhere are just normal, the starting point that leads to systems like ours with those slight misalignments.
That's the implication. It suggests these subtle tilts might be a natural outcome of the whole star and planet formation process, baked in from the start. It points towards a more dynamic origin story.
And we see other kinds of non-perfect shapes too, right? Like eccentric disks.
Absolutely.
Yeah.
Look at Fomalhaut's debris disk, that's a more mature system, after the main gas is gone. Its disk isn't circular, it's clearly elliptical or eccentric.
Stretched out.
Right. And even weirder, the amount it's stretched actually increases the further out you go, something called a negative eccentricity gradient.
Okay, that sounds complicated. What does it mean?
It basically means the oval shape gets more pronounced further from the star. And the best explanation for that kind of sculpted shape is hidden planets. Unseen planets orbiting within or near the disk, whose gravity is shaping the whole structure.
Like cosmic sculptors pushing and pulling the debris around.
Exactly. It shows how the planets themselves actively dictate the final architecture of their systems.
This even ties back to Earth, doesn't it? Specifically where our water came from. The old idea was mostly icy comets from way out, like deliveries.
That was a popular theory, yes. Comets bombarding the early Earth.
But there's new thinking on that too, related to how ice behaves in the disk.
There is. Some recent computational chemistry work is challenging the idea of a single knife-edge snowline where water ice suddenly turns to gas.
Okay, so it's not just an on-off switch.
Apparently not. This research suggests it's more gradual. Water molecules are bound to dust grains with a range of energies, so they don't all vaporize at exactly the same distance. It's more like a fuzzy, extended zone where sublimation happens gradually.
A gradient, not a sharp line.
Precisely. And when they model planet formation with this more gradual water release,
let me guess, they can explain Earth's water without needing only comets.
That's what the models suggest. They can reproduce the amount of water we think Earth has and also match hydration patterns seen in meteorites by having Earth acquire a good chunk of its water locally from material within this gradual sublimation zone as it was forming.
So maybe we didn't need all those deliveries from the outer solar system after all. Some water was homegrown.
It suggests a significant portion could have been acquired locally, yes. It highlights how these physical conditions, like snow lines, whether sharp or gradual, and other things like pebble isolation mass.
What's that?
That's basically the point where a growing planet gets big enough to carve a gap in the disk, which stops more pebbles from drifting inwards onto it.
Ah, it cuts off its own food supply.
Kind of, yeah. These concepts are crucial for figuring out a planet's final makeup based on where and how it formed in these dynamic disks. So if we try and, connect this all together,
Yeah.
step back and look at the bigger picture.
What's the main takeaway from this deep dive?
I think what's really emerged is that planet formation just isn't this single standard process we might have thought. It's not one size fits all.
Right.
We've seen the timescales can be incredibly fast, way faster than we expected sometimes.
The planetary fast track.
The chemical ingredients, the recipes for new worlds, they vary wildly. Sometimes you get deserts where you expect oceans, chemically speaking, like XUE10 with its lack of water, but loads of CO2.
Yeah, the CO2 surprise.
And the environments themselves, these protoplanetary disks, they're not the calm, flat platters we pictured. They can be warped, tilted, eccentric, much more dynamic.
So what does this all mean for you, our listener? I guess it means the universe is, well, a more creative architect. Maybe more unpredictable than we thought.
I think that's fair to say. More ingenious, perhaps.
And these discoveries, they really make us look again at our own solar system, don't they? How Earth got its water, why the giant planets are where they are. It all seems a bit less settled now.
It does prompt reconsideration. It adds layers to the story of our own origins. And it leaves us with a really important question to think about, doesn't it? If planets can form so fast,
Right.
and with such different chemical starting points, and in these dynamic, sometimes warped environments, what does that actually mean for the chances of finding another Earth out there?
Yeah. Does it make it more likely because formation is common? Or less likely because the conditions vary so wildly?
Or maybe it just makes understanding our own planet's specific complex history even more crucial.
Yeah.
It really opens up the possibilities, makes things seem both more abundant and maybe more mysterious.
It definitely leaves you with a sense of wonder and the certainty that the more we look, the more surprises are waiting. The universe keeps revealing new ways worlds are actually built.
Absolutely. The cosmic blueprints are still being written, it seems.
So what other discoveries are just around the corner? We can't wait to find out with you on our next deep dive.